Today's lecture is about scaling, and it's one of the most important in the series of lectures. So if you recall back to lecture 2 where we talked about the cypherpunks wanting to create blockchain as this institution which basically replaces all these centralized authorities, then the blockchain kind of needs to be as efficient as today's systems if it has to replace it. And today's lecture will talk about where the blockchain currently is and how it's going to get there to be at least 1/5 as efficient as what we have today. So we'll get started by talking about the background, what it means for blockchains to be scalable. We'll then talk about a naive solution and see why that doesn't work. And then we'll look at two different kinds of solutions. One is a vertical solution to the scaling problem, and another is a horizontal solution. So let's get started with some background. So what is scalability? There are multiple definitions to scalability itself, but what we are most concerned with is the ability of a system to deal with increased transaction volume. And this is measured in transactions per second, and this is kind of like velocity of transactions. How do we increase transaction volume? Well, there are two ways. One is you can increase the volume of transactions, or you can decrease the block time. And we'll talk about that in the next slide. But while that is the main definition of scalability, we also need to concern ourselves with the size of the blockchain, because blockchain is a decentralized system, and if we want to keep it decentralized, we need to ensure that the size of the blockchain is such that many people can easily download it and easily be miners. And right now, the blockchain is about 140 gigabytes, which is a lot of memory. Like, you're not going to run that stuff on your phone. You're not even going to want to store it on your Mac. That's going to take up half your space. So how do we reduce that? And that's just in like the past 5 or 6 years. Imagine if the blockchain is going to be around for a few thousand years. What's the size of it going to look like? So those are definitely two different issues, and that brings us to talk about the scalability trilemma. The scalability trilemma basically says that any blockchain-based system can only have two out of the following three. So decentralization, security, and scalability. Decentralization is this notion that everyone in the network has some average fixed computational resource, which we call C. Scalability is given that the average person has this computational resource C, how many transactions can we make per second? Like, if everyone in the network has, say, 5 gigabytes of RAM, and maybe their machines can do 100 hashes per second, can we do 1 million transactions per second in the network? And scalability is basically like how much can we push the ecosystem's capacity to handle transactions. Security is basically this notion of how well can we defend against an adversary who has resources almost as large as the size of the ecosystem itself. So to understand all of that more, we'll break down and do a little bit of math. So this graph is basically one which represents the size of a transaction over a period of a few years. And as we see right here, the average size of a Bitcoin transaction is like 546.38 bytes. So let's do some math. If the average size of a transaction is 546 bytes, and the current block size is capped at 1 megabyte, and the expected time to every block is 10 minutes, what is the transaction per second that we can have in the Bitcoin network? Well, basically we have 3.2 transactions per second. How does that compare with all the central institutions that we have today? Well, Bitcoin on average can do 3 transactions per second, while PayPal, on average, can do 150 transactions per second. And then you have Visa, which on average can do 2,000 transactions per second. And this is only considering the average case. What happens when the load is really high and in the maximum case? Well, Bitcoin cannot scale much more. It can still do just about 3.2 transactions per second as per our calculations. PayPal can do 450 and Visa can do 56,000 transactions per second. Now, how is Bitcoin supposed to replace Visa if Bitcoin can do 3.2 transactions per second and Visa is out there doing 56,000? That is basically why we have a scalability lecture and we have a lot of scaling solutions. So how do we bring up this transaction per second rate? As we discussed in the first slide, you can either increase the volume of transactions, which gives us two parameters we can play with. One is the size of transactions and the second is the size of blocks themselves. Or we can decrease the block time, which means just decrease the block creation rate, like create blocks at a faster pace. We also use different kinds of scaling techniques. The two most prominent ones that we'll be discussing in today's lecture are vertical and horizontal scaling. Vertical scaling is this notion of like adding more RAM or CPU power to your existing machine. And if you're familiar with Moore's law, almost like every 15 months you have like a doubling in the amount of CPU power that you can add. And some vertical scaling solutions that we look at today are increasing the block size, Ghost, which is Ethereum's proof of work solution, or payment channels. Horizontal scaling is a notion of, okay, if we cannot add any more RAM or CPU power, let's add more machines and of the same amount of computational power. So this image is basically a difference between vertical and horizontal scaling. And examples of those are sharding and sidechains, which we'll again look at today. Diagonal scaling is just some combination of vertical and horizontal. Some very cool examples are Plasma and Cosmos. They're both actively under research right now. If you're interested in like helping out with scaling in the blockchain world, you should come talk to me. And those are very hot areas of research. Okay, so let's get started by talking about a naive solution. Why don't we just increase the speed of blocks by decreasing the proof of work difficulty problem? Who arbitrarily set this to 10 minutes? Why can't it be 10 seconds? Why can't it be 1 second? That would just solve all our problems, right? Well, there are two notions of time, and we must understand both of them. The first is the time it takes to do proof of work and create a block. And then the second is the time it takes to propagate your block in the network. So what that means is how long will it take for Gloria or Nadir to hear about my block once I've created it. And some amount of research done on it shows that if you want about 50% of the people in your network to know of the block, it takes around 6 seconds. And if you want at least 95% of other nodes in the network to know of your block, you're going to take 12 to 13 seconds. Now, why is that a problem? Well, if your block creation time is 10 minutes, then you have 600 seconds, and your time to propagate is 12 seconds, the ratio is not too bad. But if your time to propagate is 12 seconds and your time to create is 14 seconds, that gives us a lot of problems. So for example, it makes it more beneficial to withhold blocks. So if your block creation rate is 14 seconds and it takes 12 seconds to propagate a block, if you just withheld your block for 2 seconds, it gives you an unfair advantage of 2 plus 12 seconds, which is a whole 14 seconds, the time it takes to create a block. So if you are the current miner, you're most likely going to be the next miner again. And you don't want that happening in the network. Also, if more people don't hear about your block in time, they're going to be working on the old block and on the old chain. That means all their blocks are going to be orphaned, or they're not going to get any reward for doing all that work, and you're wasting their resources. And what does that mean? Well, that basically leads to more frequent forks because more people are creating competing blocks. And that leads to a bigger problem now because it's easier to double spend. Some other cons are just decreasing this difficulty parameter is a part of the fundamental Bitcoin protocol, so you can't just introduce it with a soft fork. You need the whole Bitcoin community support and try convincing that community to do anything. If you've heard about the BLOCKSIZE debates or SegWit 2x, you probably know how hard it is to get the community to adopt solutions. Another problem is just by increasing this rate, you're increasing the rate at which the blockchain storage also increases. So, for example, if the old blockchain was growing at a pace of 5 gigabytes every 2 years, your new blockchain is now growing at a pace of 5 gigabytes every 1 year. And if you're a miner and you can't store 160 gigabytes today, how are you going to keep up with the double pace growth of the blockchain? Because now you have to store 160 plus 5 every year. And 5 is just a number I'm using as an example. Like the actual growth pace might be like 40 gigabytes a year. And that leads to centralization because only those who can afford to keep up with this pace change can remain to be miners. And you also have this other problem of initially you could wait for 6 confirmations or 1 hour, but now you have to wait for 12 confirmations, which is still 1 hour, so you didn't really solve anything. So our naive solution clearly does not work. So let's try and fix it. How do we fix it? Well, Ghost, which is Ethereum's proof of work, is basically a way to account for all these orphaned blocks. So orphan blocks are also called uncles, like we see out here. And Ghost basically decides to reward up to 7 generations of uncles. So if you are a block and you include your grand uncle, you will get an additional reward for including that uncle, and your uncle will also get some small portion of the reward. And this clearly seems to work because Ethereum has 17-second block times, while Bitcoin has 10-minute block times. This also basically changes the whole notion of how you look at the longest proof of work blockchain, because now you're considering the heaviest blockchain based on the scores of all the uncles. It gets pretty complicated, but if you want to talk more about it, come to me after class. So what about if we just increase the block size? Will that work? What do you guys think? Well, increasing the block size seems like a pretty straightforward solution, right? If my current block is, say, this small, why don't I just double it and squeeze in more transactions? Everything should work just fine. And I have an added benefit of giving all the users a lower transaction fees, because if in the earlier case, a miner was getting $50 per block because of transaction fees, now that I fit in twice the number of transactions, I can lower the transaction fees for my users. But does it work? Not really, because some of the minor problems with that is you need a hard fork to implement it. If you're a miner, if you're going to get lower transaction fees, you're not going to really be happy. There's no way you're going to be convinced to lower that rate. And you have the same problem that you did with the naive solution, which is your blockchain is still growing at twice the pace now. And that leads to centralization. The Bitcoin blockchain is already 140 gigabytes long. If you implement, say, a 2x increase in block size, sure, maybe you'll accommodate more transactions, but now you've gone from 3.2 transactions per second to 6.4. Visa is still doing 56,000. How do we get there? So you quadruple the block size, you multiply it by 1,000. Well, if you multiply it by 1,000, then your blockchain size increases at such a fast pace that unless you're super rich, you can't store it anymore. So you lose out on decentralization, and that ties back into the scalability trilemma. Other issues with that is longer propagation times itself causes attacks. So the bigger the block, the longer it takes to propagate, and the longer it takes to verify a transaction. So a few years back, there was a miner who decided to put an almost 1 megabyte size transaction in his block. So now every other miner who had to work on top of his block had to first verify the transaction, and that takes like 30 seconds or 40 seconds, by which time he has this added advantage of working on the next block, which you don't really want in a proof of work system. Also, yeah, as I said, it's just a temporary fix. You need a better way to reach Visa scale. So if playing around with the block size or playing around with the time field doesn't really help us, maybe we can decrease the size of the transaction. There are two different solutions which propose playing around with the size of the transaction. One is called SEGREGATED and the other is called recursive SNARKs. So SEGREGATED, okay, so let's talk about decreasing the size of transactions. You don't really have the same problem as you did with increasing block size, because if you notice, your block size remains the same because your transactions have just gotten to be half the size or a quarter the size. So your blockchain is not growing from like 5 gigabytes in 2 years to 5 gigabytes in 1 year. So the miners who could earlier remain miners will continue to be miners for your future blockchain. So let's talk about SEGWIT, which is one of the proposed solutions. How many of you have heard of the SEGWIT 2x debate? Okay. So the idea behind SEGWIT is, if you look at a transaction in Bitcoin, you have a signature field which takes up 50% of the block. What do you use signatures for? Well, if you recall, a miner who puts together the block has to first verify that the transaction was valid and the person who sent the transaction owned the money. But apart from that, once the miners put together the block, no one ever is going to look at the signature field, so it's just sitting there taking up half of the blockchain space. So the idea is just get rid of the signature, like remove it from the transaction data. So Bitcoin Core, when trying to propose for this, is super conservative and they didn't want to deal with a hard fork, so they came up with a bunch of hacky fixes in order to make it be a soft fork. Their ideas were the old nodes are going to see these new transactions with SegWit enabled as, oh, these can be spent by anyone. They're probably going to think you're weird if anyone can spend your money, but it's not their money, so they don't care. They'll be like, whatever, checks out, verifies it, looks okay. The new nodes, which have updated their software and use SegWit, are the ones which know how to deal with these new transactions coming in. And they basically know how to check for if a transaction is valid and how to put it together in the block, etc. So one question you might have is, if we completely get rid of signatures, how do you verify these transactions are valid? Well, one thing you can do is, just as you create a Merkle tree of transactions, you can mirror that Merkle tree and create a corresponding Merkle tree of SegWits or signatures of those corresponding transactions. And now the root of the signature tree can be an input to the Coinbase transaction of the miner, and that is all included in the block. So anyone who wants in the future can re-verify everything. Of course, not all miners have to do it. This is only for those who strongly believe in that they have to have some way to re-verify all these signatures. Questions so far? Okay. So what are some pros and cons of SegWit? Well, one is it's only a soft fork, so it's not going to be that hard to convince the community. But technically, you do need at least 95% of the community support, so good luck finding that. Another pro is it fixes transaction malleability. So transaction malleability is a problem where a transaction can basically become invalid because the signature field can slightly be modified. So if you have a check that your bank gives you and say it's dependent on your signature, if you slightly modify your signature, it's still you who's signing and it's still your check, but it just becomes, the check unique ID number changes, so the transaction which you sent becomes invalid. And that's a cryptographic vulnerability which you can solve by removing the signatures from the transaction. And that basically allows Lightning Network and sidechains to work. So that's another pro of SEGREGATED. And again, just because we mess around with the transaction size, you don't have to deal with the slippery slope again, and it gives you huge efficiency gains. The cons are, of course, it's just a one-time linear capacity increase. Once you've removed signatures from the transactions, you have half the transaction left, sure, but how do you scale that down even more? You've still just gone from 3.2 to 6.4, and that's not helping you get much more of a speed up. It introduces other denial of service kinds of attacks, and it's very ugly and hard to implement and super hacky, so you don't really want that. And there are definitely easier, more clean, clever ways to solve transaction malleability. Another issue is all wallets have to incorporate SEGWIT, because if not, you won't be sending a SEGWIT transaction if all the miners have updated their software, and then that's going to lead to a lot of confusion. So, recursive SNARKs is another solution that plays around with this transaction field. ZK SNARKs are basically zero-knowledge, succinct, non-interactive arguments of knowledge. Now that was a mouthful, but how many of you have heard of zero-knowledge proofs? Okay, so they're basically this idea that you prove to someone you know something without revealing what you know. So imagine your friend says, hey, I have a challenge for you. You have to go find Yoda. Yoda is hiding somewhere in the world. You can either send your friend this picture of Yoda somewhere in Africa once you found him, or you can tell your friend, hey, I did find Yoda, but I'm not going to reveal his location to you. Instead, here's a picture of him, but I'm going to just show his face. This way, your friend is convinced that you truly found Yoda without actually knowing the location of where Yoda is. Pretty cool, right? So the idea with scalability is you basically replace a transaction or a script transaction from Alice to Bob with this proof that you can send a valid transaction. And this proof is much smaller than the transaction itself and takes just a few seconds for any machine in the world to verify. And the fun part is it gets recursive. So a miner can include a proof instead of a transaction, and he can also include a proof of proof that he verified all those transactions in the Merkle tree together. So now your new block basically becomes the root hash of the contents of the ledger, proofs instead of transactions, which become your Merkle tree, and then a proof of proof that your previous block was verified. And this means anyone in the world can verify the whole blockchain in under 1 second. Now that's a huge speed up from where it is today. And another advantage is your average proof size is around 288 bytes, and your average transaction size is around 546 bytes. So if you replace transactions with proofs, you get to double the size of your blockchain without really dealing with icky stuff. Questions about that? But there are some drawbacks. One is, if you have to generate this proof, it takes a few hours. Like, if I'm a normal person without a lot of computational resources, I'm not going to spend 8 hours and send a proof instead of a transaction. I'm just going to send a transaction. It also requires a trusted setup. So if you recall, Bitcoin doesn't want any single trusted party. And now if you bring in this notion of, hey, let's have a trusted authority that goes against the basic design philosophy. So we've played with the size of blocks, we've played with size of transactions, we've also played with block creation rate, but we didn't really get a significant improvement in our transactions per second. So we need to change something. So one idea is let's just not use the blockchain at all. This brings us to vertical scaling off-chain. Okay, we're on time. So if you recall, one issue with Bitcoin is you have to wait a really long time. If you go to a coffee shop and you want a cup of coffee, you are going to have to wait 6 confirmations if you want to be truly safe. And at that point, you're only going to get cold coffee. High fees is also another issue. Like, if my cup of coffee costs $2.5, am I going to pay a $6.75 transaction fee on top of the $2.5? This makes it uneconomical for Alice or anyone to buy low-value items. We kind of want to create the system where microtransactions are possible, where delays are not so much. So one idea is payment channels. We're going to slowly build up to it, step by step. So the first thing is, can we have Alice and Bob make payments between themselves without using the blockchain at all? So they set up some kind of private offline channel. Well, the idea is maybe Alice and Bob both have a private balance sheet. Now, every time Alice pays Bob, the transaction sheet that they both share just gets updated. Maybe they're using Google Sheets. Maybe they're using an Excel sheet. They could use lots of different things. But they're just not using the blockchain because the blockchain has transaction fees and it's expensive. They only use the blockchain when they want to settle. So the notion is, when Alice and Bob want to open this private channel, they both set aside some deposit, and that's the total amount in the channel that's going to exist. So here Alice sets in 10 and Bob sets in 0. So the total amount of transactions that can happen in this private channel between them is $10. Once they're done, like if Alice now wants to pay Bob, say $11, she needs to open a new channel with him. So Alice and Bob now have this private channel. They send in a few transactions. Alice sends Bob 7 Bitcoin. And now Alice and Bob decide they want to withdraw their money. So they close this private channel and put stuff on the blockchain. Except you have a problem now. After paying Bob a little bit of money, Alice decides, I don't like Bob. I want to reclaim my 10 Bitcoin. And since it's just Google Sheets, no one's going to stop me. I'm just going to put the old version where I had 10 Bitcoin and Bob had 0, even though I technically paid him. What's to stop her? In our private channel build-up, there's nothing. But you can use some very clever cryptography and Bitcoin scripting to create this environment where Alice and Bob are the only 2 people. They don't need to trust each other, and they can do all this private channel payment without using the blockchain. In blockchain land, we basically call this payment channels. Payment channels are also called hash time locked bidirectional payment channels, or HDLCs. So this is an outline of how it looks. So the first very important point to remember is whatever amount Alice and Bob have put into the channel is fixed. No more can be added, no more can be removed. So the total for this channel is always fixed. You then have states or rounds of transactions between Alice and Bob. So what happens is in each round, Alice and Bob both create a secret key, which they reveal only if a new round starts. So what prevents Alice from stealing Bob's money? Well, Bob has no money. Well, what prevents Bob from stealing Alice's money? If Bob here wants to take Alice's money, he needs Alice's signature. But Alice is not going to give him her signature for free, or she's just not going to give him her signature. So Bob's not going to get Alice's money. What about if Alice wants to claim her own 10 Bitcoin? She's like, okay, Bob, we're done transacting. I'm going to take stuff and put it on the blockchain so I can withdraw this money. Well, then Alice signs and puts it on the blockchain. And now she has to wait 1,000 blocks before the money successfully reaches her. Why 1,000 blocks? We'll see in the next round. So, in state 0, if you recall, Alice and Bob both had a secret key. But once they reach state 1, Alice reveals her secret key to Bob, and Bob reveals his secret to Alice. So now, Alice decides to send 3 Bitcoin to Bob. That means Alice now has 7 Bitcoin and Bob has 3. If Alice tries to go back to state 0, where she had 10 Bitcoin and tried to claim this Bitcoin back, then Alice would need to sign and wait 1,000 blocks on the blockchain. If Bob sees that, he can basically sign, and he has Alice's secret key, so he can claim all the deposit and override Alice for being a cheater. Versus if Alice does that in state 1, she truly does own 7 Bitcoin, and Bob doesn't know her secret, so there's no way he can get her money. She just has to wait a period of 1,000 blocks. And once Alice puts her claim for reward on the blockchain, Bob will automatically be given his 3 Bitcoin. Questions on this? Yeah.
How does Bob can know that Alice has come back to the state 0 and she tries to and prevent her from getting her 10 Bitcoin?
Okay, so if Alice tries to say, oh, I don't want 7 Bitcoin, I want 10 Bitcoin, the only way Alice can claim her 10 Bitcoin is by putting this on chain. So her signature along with 1,000 blocks. Or she would need Bob's signature along with her secret key. But Bob is not going to give her his signature, right? So she would sign and put this claim that she wants her 10 Bitcoin from state 0 on the blockchain. Now Bob would see that, and because Alice has to wait 1,000 blocks, before the 1,000 blocks time period gets over, Bob would sign along with Alice's secret for that round and say she's wrongfully trying to take my money, so I'm going to slash her and I'm going to get all the money instead. That's how Bob prevents her from taking unfair money. Does that make sense?
Yeah.
Okay. So one observation is that if Alice or Bob try to cheat each other, the other person can always override and take all the money in the deposit. But if Alice and Bob are cooperative, they never have to touch the blockchain. Everything goes peacefully and smoothly. They can make hundreds or thousands of transactions off-chain and only have to touch the blockchain for settlement and for opening. And that provides huge amounts of scalability. One issue, though, is Alice and Bob need to have their capital locked up in this private channel. So if you recall, whatever amount Alice and Bob deposit initially is all that the channel has, and until one of them claims their money back, it's locked in this private channel. So Alice cannot use the money which Bob sent her to go buy coffee from Charlie. Another issue is with payment channels, Alice can only send money to Bob. What if Alice now wants to send money to Charlie? Does she need to open another private channel with him? What if she's only going to make one transaction with Charlie? Well, if Alice is going to send money to Charlie, but she's not going to spend a lot of money. Like if Charlie would say Amazon, and you're only going to buy one product from Amazon and never use it ever again, why do you want to open an account or a private channel and lock up your money and go through that entire process? Instead, you can ask Bob, hey Bob, do you know Charlie? Can you open a payment channel with him? Can I send you money and will you send my money to him? That's basically the idea of Lightning Network. So if Alice wants to pay Charlie, she just pays Bob, Bob pays Eve, Eve pays Charlie. How does that work? Well, Alice sends a promise to Bob that she's going to pay him. Bob sends a promise to Eve. Eve sends a promise to Charlie. All of this is of the same amount that Alice is going to pay Charlie. Now Charlie then sends back his secret from that round to Eve, who upon receiving that forwards it to Bob and then Alice. And now as soon as Alice receives the secret, she sends her payment to Bob, Bob sends it to Eve, and Eve sends it to Charlie. That's kind of how the Lightning Network works. So can we do this securely? What we saw, using commitment schemes and HTLCs and some very cool crypto, we can. And that's basically what Joseph Poon and Tad describe in their white paper. So what does Lightning mean for scalability? One, it means if there's enough money, it means you can make payments. So if I and Gloria open a channel, and I put in 10 Bitcoin, I can send in money to Gloria of any value up to that 10 Bitcoin. Another huge advantage is payments are now instantaneous. I don't have to wait for a miner. I don't have to wait 10 minutes. Payments are at the rate of the internet. Like if my internet can take packets in 12 seconds, my payments are made in 12 seconds. Also, you only use the Bitcoin blockchain to settle disputes. So you're only using it for 2 transactions. One is opening and one is closing. So that means you don't have to pay any more expensive miner fees. So if I go to Cafe Strata every single morning for my coffee, I can open a payment channel with them and pay them every morning with no additional transaction fees. This basically enables micropayments. What does Lightning mean for scalability? A few other things are, one, you increased your transaction rate from 3 transactions per second to now almost 10,000 plus transactions per second. And this is true for not just Lightning, but pretty much any payment off-chain system. And you do this by taking everything into a private channel or a private bookkeeping system. And as long as people are cooperative and trustworthy, 99% of the time this works out well. Another huge advantage is sending packets across the internet is cheap, so that means sending transactions is also pretty cheap. It's probably just as much as you pay for your internet bill a month. The only expensive operation is opening and closing of channels. So some issues with Lightning are, one is nodes need to keep a very large amount of capital locked up. So if I want to pay Gloria 11 Bitcoin, but we only have 10 in our private channel, and payments are only going one way, from me to Gloria, then I need to open up another channel with her. That's problematic. Another huge issue is if I want a lot of people to send money through me, I need to have a lot of capital, because that's the only way I can make everyone's payments. And you sort of go towards this hub and spoke network topology where if there are fewer nodes in the network, less capital is required, but the more nodes there are, it leads to centralization, because only someone who can afford to be this point through which everyone goes through can put up that capital and can make all these payments. And that leads to a huge security issue. So if I'm a millionaire and everyone is sending money through me to other people in the network, tomorrow I can say I refuse to send any of your payments. I deny service. And that will cause the whole network to break down, because the only thing they can do now is open private channels with each other. So far we've been talking about vertical scaling, or this notion of adding more CPU RAM to every single machine. But let's talk a little bit about adding more machines to the network. So that brings us to sharding. Sharding is this idea of not requiring every single miner to work on every single block, but instead sort of parallelizing the whole process. So maybe you could have a whole setup where you have some miners work on some addresses or transaction addresses. So for example, you could say all the miners in America work on addresses of transactions 0 to 100. All miners in China work on transactions with addresses 100 to 200 and so on. So now if you're creating a block, instead of creating a Merkle tree of transactions, you create a Merkle tree of Merkle trees of transactions. And these Merkle trees of transactions are given to you by each of these different countries. So USA gives you their little Merkle tree, and then China gives you their little Merkle tree, and then you Merkle these Merkle trees. There's a lot of active research happening in sharding. A few drawbacks of it is that right now there's no way to communicate between shards. Again, if you're interested, you should definitely read more about it on the Ethereum white paper. That then brings us to this idea of sidechains, which is Bitcoin's sharding, which actually works. The idea is, if you can't speed up the Bitcoin blockchain, why not just create a lot more blockchains? So that way you kind of divide up the load across blockchains. So maybe you have this one specific blockchain which does 2-minute transactions, but it's not super secure. But if I could just transfer $2 worth of Bitcoin onto that chain to buy my morning coffee, I'd be okay with that, because hey, if someone wants to double spend me for $2, it's their choice, it's not mine. This concept of sidechains is great for experimental blockchains. So someone could create a sidechain for microtransactions, someone could create a sidechain for maybe skateboards. So it's a very Internet of blockchains kind of idea. The pros are you have less things on the Bitcoin blockchain, but can still be pegged to it. And the cons are you lose security, because your hashing power is now split up across all these chains. So whoever is a miner in the Bitcoin blockchain now starts mining on all the other chains instead of Bitcoin blockchain. So obviously you're going to have some lower threshold of security. And this is an image of the Internet of blockchains, or sidechains. So you have the main blockchain right here. Then you have a sidechain that does micropayments right there, one for beta releases. And the communication between each sidechain is through a two-way peg. So a two-way peg is basically two one-way pegs. The idea is if you have some Bitcoin and you send it to some script, it locks it up so that you cannot use it. And this proof that you sent it to that script now allows you to redeem the same amount of Bitcoins on this other sidechain. And that you can use on the other sidechain. Now, if you want to come back from, say, your micropayments chain back to the Bitcoin blockchain, you just need to prove that you sent your micropayments sidechain Bitcoin to a locked address, and then you can get the same amount of Bitcoin back. However, the whole concept of sidechains has a lot of security issues. Like, for example, I could create a sidechain where I'm the only miner and then create 60,000 Bitcoin on my sidechain, peg it to the Bitcoin blockchain. Now, all of a sudden, do I have 60,000 Bitcoin? Apparently, I do. And maybe tomorrow I can just short the currency. So, all those are definitely flaws of the sidechain model, but it's an interesting solution. So, we've looked at different kinds of scaling solutions. Bitcoin and blockchains basically have this huge scaling issue. We saw how we went from 3.2 transactions per second to about 10,000 transactions per second with Lightning. If Bitcoin needs to be able to replace Visa or any of these other central institutions, it basically needs to be as efficient or more efficient than all of these. So that's pretty much it for today's lecture.